we were looking at circuit representations of two ports, in particular passive two ports whose two port parameters are symmetrical, right. So, for them it was easy. If you have any resistive 3 terminal two port, this can be equivalently represented with a pi network which consists of 3 resistors like this. Okay. Or a T network okay. Now, these things sometimes make sense, more sense than using the ones with control sources, because you have a purely resistive network and then you represent it with some other simpler network which also is purely resistive. Okay. So, it may be more intuitive to understand in some ways. Okay. And sometimes, I mean, this in a different context, this is also drawn like this, right, a triangle, and it is known as a delta network, and this can be written as a, to write it in an angle, this is known as a star network. And then you have these formulas which take you between star and delta networks. Okay, it's exactly the same thing. Whatever you need to translate between the y and z parameters, that's exactly what you will have. Okay, we'll take it upon as an exercise a few minutes later, right. So, we can represent the same network either as a pi or a t. Okay. Any questions here? So, if you have a circuit with real resistors, you do know that Y12 will be negative. So, this network will consist of only positive resistors. Similarly, the T network. Okay. Now, by the way, the Z or Y matrix, Z or Y parameters of two port will be symmetric even if you have negative resistors. Okay. That has got nothing to do with passivity, right. Even if you have negative resistors, that will be true. Only if you have control sources, it is not necessarily true. Okay. I think in the tutorial you also saw many examples. With control sources, you can make things reciprocal, but it is not necessarily so. Whereas, without control sources, it will be reciprocal. Only thing is, I mean, if you have negative resistors, this Y12 is not guaranteed to be less than 0, because the network itself could be generating power. Okay. Now, what I was asking towards the end of the previous lecture was, so let us say this is not purely resistive. Okay. This becomes like more general, it also has control sources. So, what will happen then? This makes it makes the y parameters not symmetric. Y12 is not necessarily Y21 and Z12 is not necessarily Z21 and so on. Okay. Now, we already know the circuit representation of some such network, right. You have 2 resistors and 2 control sources. But what I am trying to do is, can we tweak this network just slightly so that it will represent the general 2 port network? Is that possible? What would you do? So, let us take the y parameter example. Now, we have this, and these two are not necessarily equal because of the presence of control sources. Okay. I know that when they are equal, this representation will work. So now can we modify this slightly so that it will work for the asymmetric case? It's quite easy, just think about it. What would you do? What would you do? Okay, one suggestion is you replace this with a y12. Okay, replace this with a dependent source. What kind of dependent source? Voltage control current source. In which direction? Okay, and what's the value? What's that? Plus will this work? I mean, essentially you have replaced it with two control sources. It will probably work also. Okay. I am not sure if this is the right form, but that could work. Or I think the other suggestion was to add a control source here, or maybe on this side. If I do this, what would that have to be? Yeah. So this y21 minus y12 times V1. Okay. So that will work. Essentially, you have 4 parameters, right? So you need basically 4 different parameters to describe the network. So earlier representation had 2 resistors and 2 control sources. Now we have 3 resistors and 1 control source. That is also fine. And similarly, you can see that very easily for the Z parameter matrix. If you include Z21 minus Z12 times V1, that will also work. All that will do is it will cancel off this Z12 term here and then introduce a Z21 term. That's all. Okay. Earlier they were equal, so that was okay, but now you need them to be unequal. So the network is also asymmetric. But from this you can also see that there is an infinite variety of possibilities, right? You can keep on generating networks. The more important thing is to see in your context if some particular representation is more useful than others. Okay. Consequently, this is a general representation. Okay. Voltage source. It is it's I1. Yeah, that's right. Okay. Thanks. Any questions about this? This is yet another possible representation of 2 ports. All this start making sense when you start analyzing circuits. Some things are easier to handle than others. Okay. Like I said earlier, this pi network is equivalent to this T network, this pi, which is also known as delta network, is the same as T or the star network. So between these three terminals, they are exactly the same. Okay, and sometimes while doing circuit analysis, it may be easier to analyze with one form or the other. Okay, depending on whether things are connected in parallel with this or in series with this and so on. Okay, so that's why there are the star to delta for transformation formulas. So by the way, these Y's are the conductances, right, and these Z's are the resistances. So let's say these resistances are labeled RA, RB, RC in the delta case, and R1, R2, R3, or maybe let me change the notation here. Let me call this R12, meaning it's connected between 1 and 2. This is R31 and R23. Okay, those are the resistance values. So what I want you to evaluate is what are known as star delta transformation expressions, that is R12, R23, R31 in terms of R1, R2, R3, and also in the other direction. Okay. Now you can do this anyway. There are lots of ways to do this, but these expressions are already given, right? So it must be quite easy to do. You know that the Y parameters are the inverse of the Z parameters. Okay. So I mean basically eliminate these Y's and these small Z's and get the expression in terms of for these things. Okay, you get some bunch of symmetrical relationships. Okay, so please do this. Is the question clear? I denote these resistances by R12, R31 and R23, and these by R1, R2, R3. Okay, what I want is for these two networks to be identical. What should be R1 in terms of these three resistors, R2 in terms of those three resistors, and R3 in terms of those three resistors, and so on. Okay, so please do that. You can do it any which way you want, but I think using the already known inverse relationship between Y and Z parameters, you will be also easily able to do that. What did you get to with answer? Let's say for, I don't know, so which one did you calculate, which way? Let's say you design these two resistors R2 square R3 square divided by Z12, which is R3. Okay. So this comes out to be the pairwise products R1 R2 plus R2 R3 plus R3 R1 divided by R3. Okay. This is fine. This is okay. That's why I said if you start from Y12, it may be easiest. So essentially, the resistance between these two terminals, 1 and 2, is the sum of pairwise products divided by the resistance connected to the other terminal, right? Between 1 and 2, you have in the denominator R3, whatever is connected to R3. And from the symmetry of the network, you will see that what would be R13? What would change for R13? The numerator will be exactly the same, right? The only thing that is distinguishing which terminals is this one, that becomes 2, R2. And similarly, basically if this was R31, here you would have R2, and if it was R23, you will have R1. Okay? Numerator will remain exactly the same. Any questions here? Okay. And how do you go the other way? What would be the easiest? I mean, there are so many things. I think I saw many of you getting the right expressions. What would you start with to go from delta to star? Calculate Z12. That seems like the easiest, right? This Z12 is the same as R3. So R3, which is Z12, and this is equal to what? Minus Y12 by, sorry, the other way around. Oh yeah, this is correct. So Y12 by Y11, Y22 minus Y12 square. And how much is Y12? Minus R12 divided by Y11, Y22. How much is that? circuit 2 and so on. So let's say you have not heard of 2-port parameters, you could do it that way. Make sure that they are equivalent and you will get a circuit. Okay. So these we will use later when we come to 3-phase systems. We will have loads which may be, I mean, I think you have heard of 3-phase systems even if you don't know what it is. You will have 3-phase power transmission, right? So you will have loads connected like this between the lines or from the line to the start point and so on. And there are different loads. So if you have different loads, they are all connected in parallel. So the best thing is probably to convert everything to the delta form and then add up all the admittances. Okay. So that's why these transformations are useful. Any questions here? Just one more form of, you can think of it as one more of the 2-port equivalent formula. As far as we are concerned, that 3-phase, 3-terminal network is another 2-port, and you have this form of the 2-port with 3 resistances in a delta and this form in a star, and to make the 2-port parameters equal, you will have to choose the resistors in certain way. That's what this formula tells you. Okay. Any questions about this? We have discussed a number of things about 2 ports. Let's, this would, I think, be the last topic. So let's say you have some network N, and let's say it consists of only resistors, and I'll show one particular resistor outside. Okay, inside it can have any number of resistors or not. And let's say I connect a voltage source to this side. Okay. So now, and it is drawing a certain current, right? Now the question I want to ask is, so let's say this particular element changes by certain amount, delta R. Okay. You expect that this current will change, right? Something has changed in the circuit, so you expect some current to change. Okay. Now, can you tell me how much delta is? Of course, you can go and reanalyze the whole network, but could you do it in a different way? By, let's assume that the original circuit has been solved. This is available. So now from this, would I estimate delta I when a particular component changes? And you can see why this is interesting. There are many reasons why components change. Okay, like one possibility is, let's say you have a network that's intended to perform a certain function, and at least you know that with temperature resistances change and so on. So you may have to find out, like, what is the effect of that? Will the function that you designed work as designed, or will it go out of bounds in some way? There are many other reasons where things will change. One of the other things is that, let's say you specify a number of resistors. So let's say your circuit uses like 100 1 kilo ohm resistors. It's not that every resistors will be exactly 1.0000 kilo ohms. Okay, each one will be different in some way. Okay, this is known as mismatch. Now they may be off by 1%, they may be off by 0.1%. That depends on the construction, but they will be different. And there are circuits in which that will also affect the performance. Okay. So in general, it is of interest to find out if some component changes, what is the effect. And here I have taken a particular quantity. I have the driving source V here. The current drawn from that is what I am looking at. So could you find out the change if the original circuit solution is available, and using some circuit theorems that you already know. Okay. Please try to do this. It's a little open-ended, but I'll just give you hints. So you could use substitution theorem. Just figure out what is it that you will substitute. okay, and then could use some approximation, it will become kind of obvious. It's the kind of approximation you do all the time. Then maybe, I mean, you have something on the left side and something on the right side, and a weapon of choice when you have that is reciprocity, okay, because original circuit solution tells you if V is applied, what would be flowing here, okay, and now you want to find out if some change happens here, how it gets reflected to the other side. This looks like the choice problem for reciprocity, right? So try to do this. First of all, what will you substitute? What will you substitute theorem for? So if this R naught is changed to R naught plus delta R, you expect everything in the circuit to change. Okay, so let's say this changes to I plus delta I, and this changes to I naught plus delta I naught. Okay. Then what you can do is this R naught itself you can split into two resistors in series, R naught and delta R, right? This is trivial. Now you can substitute this delta R by what? What will you substitute that by? I mean, just said you will substitute delta R. What will you substitute it with? A voltage source I naught plus delta I naught times delta R. Okay. So far, I mean, I have made very trivial manipulation. I just wrote R naught plus delta R as two series resistors, and this substitution is exact. Where is the approximation now? Yeah, this is a common thing that you do, right? You product of two deltas, you just neglect. That's a, so that this problem doesn't involve the change solution. That is what you are trying to find, right? So you neglect this. So this will be approximately equal to I naught times delta R. Okay. So now if you think about it, the original solution is due to this source, right? And the change delta is due to this one. And what is it that you are required to find? What is it that you are required to find? This delta I here, okay? Now I can write this as two separate pictures, right? I will first set this source to 0, then simply I will get the original solution. This is the original circuit which has already been solved. Then I will set this source to 0. What will I get? Only the deltas. Okay. Then what? What will I do now? Voltage source in? No, I mean it's already solved, but what is the answer? Where does reciprocity come in now? It's already done, right? If you think of this as one of the ports and this as the other port, in this case this is short circuited. Okay, so the current going this way divided by the voltage here, that is what? Y12 or Y21 of that network. Okay, and how much is that? What is the current flowing this way? Minus I naught divided by V, and that is exactly the same as, if this is port 1, this is port 2, the current going that way, which is how much? Delta I divided by the voltage across port 1. The port is not here, that is all. Okay. Divided by what? I naught times delta R. Okay. Is this correct or no? So, delta I by I naught delta R equals minus I naught by V. Is this fine? Is it okay? And some of you represented this whole thing by a Thevenin network. That is fine, everything is fine, but then you have expressed the answer in terms of VTH and RTH, which is something else you have to find. Okay. But the same thing can be got. This I naught itself is dependent on VTH and RTH, right? Because if you replace this whole thing by its Thevenin equivalent, you will get VTH, RTH and R. What is the value of I naught? VTH by RTH plus R. So, I think in fact it is this that appears in the expression. So, that can be substituted by I naught, so that you can simply write it in terms of the solutions. Is it okay? I think there is some way to get that also, because here we will get delta I to be minus I naught square delta R divided by V. Okay. And this can also be written as, this I naught itself is the original voltage across this, right? If that is V naught, this I naught itself is V naught by R. So, this will be minus V naught by R time, sorry, V minus okay. Now, many ways to express this, but you get this delta R by R here. So, it is related to the fractional change in the resistance. Okay. This is known as the compensation theorem. Basically, if you want to evaluate the effect of small changes in components somewhere, you do not have to reevaluate the whole circuit. Okay. So, you express that as some source, and then you will get this whole. Okay. I mean, there is nothing wrong with, you can say what is wrong with resolving the whole circuit, I can do it. But maybe you are asked, like let us say there are 1000 resistors, and you are asked like what happens if there is 1% change in this, what happens if there is 1% change in that, and so on. So, you do not want to sit and like resolve like 1000 new circuits, right. As far as circuits are concerned, each time a resistance value is changed, that is a new circuit. Okay. You do not want to set up the whole matrix equations and resolve everything. If you know that the changes are going to be small over a certain original circuit for which you know the solution, you can use the original solution and some slight approximation like this to find the sensitivity. This is like finding the derivative, right. Derivative, we are told that it is small change divided by small change as the change is going to 0. As the change does become infinitesimal, it becomes exact. Here also it is the same. Okay. So, if let us say 1 kilo ohm resistor changes to 1.1 kilo ohms, you will get some solution, and you evaluate it using this approach, you will get a slightly different one, because the delta is 100 ohms, it is 10%. It is not actually, the delta I times delta R term may not be negligible. But as the change becomes very small, the 1K resistor becomes 1.001 kilo ohms, that is, it changes by 1 ohm, it becomes closer to the actual one. So, it is somewhat like finding the derivative, that is all. Okay. The other ways to derive this also, just think about it and see. Okay. Yes. consequence of I don't know. I mean, energy conservation is very general. Yeah. So actually, there is a particular theorem for any electrical networks. I didn't talk about it. If we have time at the end, we'll do it. It's known as Telegan's theorem. It says that if you have two graphs, I mean, if you have a graph, right, and the circuits can be anything. You have two circuits with the same graph, then sum of Vk Ik hat is 0, where V is taken from one circuit and K is taken from the other circuit. Okay, this looks vaguely like the conservation of energy, although V is from this circuit and I is from the other circuit. Okay, this is just a consequence of KVL and KCL. So I don't know what to make of the statement that this comes out of conservation of energy. Probably everything comes out of that. So I have to think about it a little more. But it's not true that I mean, when you change some resistor, the energy supplied by the voltage source and so on do change. So I'm not sure how to apply the conservation of energy here. Okay. In fact, conservation of energy, I'm sure you have seen those problems. There are some problems for which you get very neat solutions with conservation of energy if you know that you had applied there. But actually, it is quite hard to, at least for me, not easy to know when to apply this conservation of energy principles. You have to account for energies properly. Right? So here I don't know whether it's related to the conservation of energy directly or not. Okay. I think in general, when you use conservation principles, you have to define a system in which the energy is conserved and get it from there. Here, because all this reciprocity and so on can also be derived from Telegan's theorem, probably like you start from conservation of energy, you derive Telegan's theorem, you derive reciprocity, and you can derive this. So that way everything is resulting from there. But beyond that, I don't know.